Final talk of the day. We made it. It's an exciting one. The Anatomy of Distributed Systems by Tyler McMullen, who comes from Fastly. Tyler, please come to the stage.
Hello. Cool. So I didn't actually make the title of this this presentation just to fit this picture, but I was really jazzed when I found the picture. I'm like, oh, this is perfect for this. As mentioned, I'm Tyler McMullen, TB McMullen on Twitter. Feel free, if you disagree, to argue with me. I love to be told I'm wrong. It's super great. I'm the CTO of this company, where we make lots of distributed systems and actually use a whole bunch of Hoshi Corp stuff. So ultimately, one of the points of this talk is it's kind of like a thank you from me to Hoshi Corp for making the building blocks of distributed systems, right? In the past, you've always had to develop a lot of those things from scratch. And so I'm super jazzed to not have to be able to, or not have to build, say, a failure detector to build a distributed system anymore. But anyway, okay, so I figured we would have a nice chill talk for the last talk of the day, keep it light. Just kidding, let's build a distributed system together. So if this seems too intense, again, you can blame Hoshi Corp. They said that this is supposed to be a deeply technical event, and I am not fucking around with it. So a lot of the talks that I hear about distributed systems are either theory without implementation or implementation without theory. So this is kind of my attempt to bridge somewhat of a gap there, and we'll see how much of it I can fit into 40 minutes or 30 minutes or however long this is supposed to be. Right, okay, so the project that we're gonna kind of try to design together is something that's pretty specific to Fastly, but a lot of the principles actually apply to many, many other distributed systems. So I will jump right in. Right, so Fastly works as a reverse proxy, essentially, right? So on the left, we have a user. On the right, we have our customer's origin server. And in between in the middle, we have one of our data centers. So a request comes in and then passes through. We make whatever modifications and goes straight through to the origin server of our customer, right? So if you're going to say NewYorkTimes.com, you actually hit our servers first, and then we pass it on to them, right? So easy enough. But however, it's not ever, or rarely is it just one origin server, right? It's actually multiple origin servers, so we have to load balance between. Also, by the way, I really kind of went nuts with the keynote animations on this one, so it's going to be great for me, I guess. I don't know. So, right. So in this case, we actually want to pass traffic through to load balance among multiple of these, like so. However, of course, if you have multiple servers, you have to do something when one of those servers starts to fail. So what we're actually going to be designing today is a health check system, because obviously we don't want that to happen, right? If the request comes in, we don't want to send it to a dead server, right? We would instead, of course, prefer to send it to a live server. Seriously, just a lot of keynote animations. But of course, so we don't just have one data center at Fastly, we have many data centers. And so, of course, all these different data centers are going to be doing their own load balancing among all of the different origin servers that we're talking to. One of the tricks with the internet, though, in general, is that every data center, every place where you are on the internet has a different view of origin health. Right? So if they're all up for one, that's fine. However, from another point of view on the internet, one of those servers might look like it's down due to routing or the asynchrony and complexity of the internet. But basically, the point is that from where you're standing on the internet will change your view of the health of a server potentially, right? So that means that basically we're going to need to divide this up by data center. Great. So that's the first step, essentially, is what we're going to. But of course, within one of those data centers, they're not just a single system, right? It's a whole bunch of servers. Okay. So interestingly, this is again, this is one of the things that makes it kind of specific to Fastly. But individual servers, because we are a multi-tenant system, may have different views of which origin servers exist at any one time, right? We don't have every service running on every server at all the times, right? So as we're going through, some servers will know about some origins and some won't. Like so. Man, really love those keynote animations. Right, okay, so In addition to just being a health check system, we also have to have some way of figuring out which servers should own which origins. Kind of like this, right? So like we have all of our origin servers on the left here, we have our servers in the middle, and we need some way to like spread them among all the different servers. Ideally, we would only actually have one server in each data center doing health checks at any moment, right? Because if we had like 1,000 servers all doing health checks against our customers' origins, maybe once a second, suddenly that customer is getting 1,000 requests per second to each server, right? They're going to have a bad time. That's basically DDoSing our own customers. We don't want to do that. So we need some way to spread the load across all the servers and then also communicate the shared state between all of them so that they can all make reasonable load balancing decisions. One of the problems, of course, is that our servers also die, right? So if one of our servers dies, we need some way to distribute the things that that server owned, distribute that work across the remaining live servers. We need to be able to do that as multiple of them fail. So we need to do this across 50 plus data centers, thousands of bare metal servers, 64 servers per data center across tens of thousands of origin servers. Okay, let's go. So to recap, we have a system which needs to keep track of origin health per data center, despite each server having different views of the origins. The system needs to handle server failures gracefully, it needs to stay in sync, and it needs to ideally only have one server doing health checks per data center at any one time. All right, is everyone still with me? Good? All right, right on. Okay, so here's one possible solution. You know, we could just use console. This would actually make the system, that would actually make this problem a lot easier. One of the things about console, though, is that in CAP terms, it's a CP system, right? It's a consistent system. In other words, it's a linearizable system. Or for our purposes, you could use this for atomic broadcast, right? Basically, atomic broadcast meaning like either all nodes see the request or the message that goes out, or none of them see it, and also they see it in the same order. This would ensure that all nodes have the same view at all times, and because it essentially gives events a total order, it also means keeping things in sync is a lot easier. However, this would be a very short talk if I were just going to say use console. So in my opinion, I would argue that in this case, console is actually too strong of consistency for this problem. Of course, it comes with trade-offs, right? In other words, in the presence of partitions, we can choose availability or we can choose consistency. And console chooses consistency, which is a totally reasonable thing. And for a lot of problems, that's the right way to go. But for this problem, I think that's just not the right trade-off to make. So what we need to do is build an eventually consistent system. Okay, so what do we mean by eventual consistency? So the idea in this case is that each node in the system needs to be able to make forward progress regardless of the state of other nodes, regardless of communication with other nodes. In other words, it's like some form of coordination avoidance. Like obviously we need to communicate between each of the nodes, but we want to make sure that we don't block progress by having to communicate. Okay, if you would like to read more about this, Coordination Avoidance in Database Systems by Peter Bayless is a great paper, so highly recommended. But essentially, so like if we can't just like rub some Raft or Paxos on the problem, then what can we do? If we can't rely on ordering or atomicity to solve our problem, I guess what we need to do then is to decide on which invariants we need and which we don't, right? Okay, let's talk about causality. Rather than assigning a total order to the events, saying that like, oh, okay, despite the fact that things are happening all at the same time, we're going to like serialize them, we're going to linearize them and put them all in order, we can assign a partial order to events, which is what you can get with causal consistency. It allows us to say that some events happen before other events, or say that, okay, these events actually happen concurrently. So as an example, let's say we have two actors here. We have Jack and we have Jill. Okay, and so Jack says A, and Jack replicates that to Jill, and Jill says, okay, cool, A. Jill's like, actually, I prefer B, right? So here we can say that A happened before B. Easy enough. Jill replicates that back to Jack. Jack says C, and Jill simultaneously says D. Okay, well, we can say that both B happened before C and B happened before D. However, C is concurrent with D, right? So it assigns a partial order. Like some things happen before, some things happen after, and some things we allow for the fact that they happen at the same time. In some ways, this is in fact just how the world actually really works, right? So it's rather than like trying to assign this like linear order to everything, we go like, okay, let's just accept that the world actually is more complicated than that. All right, we'll come back to causality later. Let's talk about ownership now. All right, so to recap, again, we need to spread those origins around to all the servers. When one of them dies, we need to know where they're going to move next, right? We need to move them to live servers, like so. So let's talk about rendezvous hashing. All right, so rendezvous hashing comes from this paper, a name-based mapping scheme for rendezvous. Comes out of the University of Michigan in 1996 and was invented concurrently with consistent hashing, which I'm guessing a lot more people in the room probably know about. I see like a couple head shakes, good. And also is similar in goal to consistent hashing. And the idea with this is that you map objects to specific servers. However, when that server fails, the minimum number of objects move. Essentially how it works. So here's how this would work in our case, right? It looks kind of like that. The H is just a hash function we decided upon. This could be like murmur, or it could be like, I don't know, SHA-256. Doesn't really matter, it's just a hash function. The S in this case is our set of live servers. Great. And so the N there is just like one specific server. The O is referring to some specific origin server that we are trying to decide the owner of at this moment. And our weights, or the W here, is the weight or priority that that server will be given for this particular origin. So what we end up with at the end of this is a list of priorities. So for some particular origin, the list of servers might go, okay, first we'll start with server 2. That's the highest priority. If server 2 is up, we're going to put it there. If it's not up, we'll move it to server 3. If that's not up, we'll move to server 1, and so on, and so on, and so on. And for a different origin server, it would look entirely different. All right, so that's rendezvous hashing. All right, so to recap here, we're going to do an eventually consistent system using causal consistency. We're going to use rendezvous hashing to assign ownership. Okay, let's talk about failure detection next. All right, so if we're going to communicate in the cluster, if we're going to share state between all these things in the cluster, and also if we're going to be able to move work from one node to another node, we have to know which nodes are in the cluster, which ones are not, which ones are alive, and which ones are dead, right? Oh yeah, animations, man. So there is a classic paper, and there are actually like multiple kinds of failure detectors. You could give an entire talk just about failure detectors, but one of the more popular ones at this point is one called SWIM. And so I'll just walk through like roughly how SWIM works. There are people in the room right now who actually work on SWIM who would be able to explain this part way better than me. But let's do it anyway, right? So the idea is that like every so often, you have all your servers in your cluster, and every so often one will choose another server at random and say, hey, you up? Hopefully that server responds and everything's good. So now we know 3 is still up, right? And now we'll broadcast that around as part of our gossip system, and all the nodes will know 3 is still working. Great. Occasionally, things won't go quite as smoothly. 1 will try to ping 3, say you up, won't get a response back. And so then 1 will try to do it in a different way. It will pass it off to a random subset of other nodes to say, hey, can you ping 3 and see if he's still around? And so they do. And ideally, they get a response back, and we know 3's up. Cool. And occasionally, things go much less smoothly. Get no response, try the other path, and we don't get a response. So we now know that server 3 is down. Great. So that's a super high level description of how SWIM works. Actually implementing it is like pretty precarious and is very fiddly. Luckily, our gracious hosts for the day have already written something that does this for us. It's called Memberlist and exists as like part of, it's actually a library which I use regularly, which is great. But it's also used as like a core part of Surf and Console. So you're using it pretty frequently if you're using many HashiCorp things. But OK, great. For our example, let's just use that. That actually solves this problem for us. All right. So we have a way of load balancing and determining ownership via rendezvous hashing. We know we're going to use causality for this. We'll use swim via Memberlist for failure detection and cluster management. But of course, we also need a way to communicate, right? All right. So everyone here is probably at least a little familiar with the concept of gossip, right? Yes, so many head shakes. It's basically just the idea of like periodically and randomly passing messages within a cluster in order to make sure that it eventually and like fault tolerantly gets around to all the nodes. Great. Corp also made Surf. Super cool. So what's neat about Surf, among other things, is that Surf is actually partially already causally ordered. It uses Lamport clocks for this. However, for our purposes, we could actually use something slightly stronger, which I will get to shortly. Surf is also a push-based gossip system, which means randomly gossiping just means sending messages at random to another server. It's kind of a single-step system, which is nice. Another way of doing gossip is actually a pool system, where instead of just saying like, oh, here's my messages, instead you say, hey, can I have some messages? You pick a server at random to ask for messages from. Great. So there are advantages and disadvantages to both of these. Push gets messages around to most of the cluster really rapidly, but then takes a while as it levels off and tries to get those last few nodes that haven't seen the message yet, and you're just kind of randomly trying to get to them. It's kind of the downside of push, among other things. Pool, on the other hand, is interesting because it takes a while for it to get kind of bootstrapped. It takes a while for it to like get around to like half the nodes, but once it's around to about half of the nodes in the cluster, it gets around to the rest in like log n steps, which is really rad. Another advantage of pool is that it makes it easier for us to get a stronger form of causal consistency, which we will get to shortly. All right, let's talk about convergence. Wow, I'm actually going through this way quicker than I thought I would. That's awesome. All right, again, we're making a eventually consistent, causally consistent system using rendezvous hashing for ownership and load balancing, swim via Memberlist for failure detection and cluster management, and some form of gossip for communication. Okay, that's like much of our system, but we still need to talk about how to keep everything in sync. So let's talk about lattices. So this is a data structure, kind of. It's also a mathematical concept, and specifically we're talking about something called join semi-lattices. What that means is that it's a lattice on which you can perform what is called a join or a merge or a least upper bound function. We'll talk about what that is. But like visually, you can kind of envision a lattice to look kind of like this. You start from a root or a bottom, right? It's an empty value in the data structure. And then from there, you can diverge. You can evolve the value of this data structure. And so maybe in this case, we went off to like 3 separate branches, right? However, what makes it a join semi-lattice is that then you can apply a function and join those branches back together. And the idea here is that you can always do this. You can always like merge 2 things back together in a join semi-lattice. So like a good example of this is like a set data structure, right? So I can put A into a set and you can put B into a set, and we could both like have our 2 sets and we could like allow them to evolve over time however they see fit. You can always union them though, right? So like a basic grow-only set is a great example of a join semi-lattice. However, there are much more complicated ones as well. Right, so the idea is that we can continue to merge and branch as much as we see fit. So it turns out that lattices are super useful for modeling causality. Let's see how. There's this thing called a version vector. How many people here are familiar with version vectors? 1, 2, all right, cool. Okay, so let's talk about version vectors then. We'll do this as what's called a space-time diagram. So here on the left, we have our list of servers. We have S1, S2, and S3 for our servers, which means that when S1 decides it's like, okay, an event has happened on this server, some event. I have modified my data in some way. Right, so given that it's S1, we modify the first element of this version vector. We increment it, right? So like an event has happened on server 1. Great. So then server 1 replicates down to server 2. Cool, so it's replicated, so now server 2 also sees server 1's first event, and they have the same version vector. From there, we could have 2 events that happen simultaneously on S2 and S3. And so S2 and S3 also individually increment their specific parts, their specific elements of the version vector. So we have 1, 1, 0, and we have 0, 0, 1. Cool. Can merge that back in, and now we can see that like S2 in this case now actually has all of the events that have already happened on the system, which was 1 on each server. And then of course we can continue from there and continue to modify it. So how does that actually work with lattices? Well, it kind of does, right? So we start from a root or bottom value, which is just zeros for every element of the version vector. And we can allow those to diverge however we see fit. And as long as we have some way of merging them together, you can use this for modeling causality. Pretty cool. All right. So how do we use all of that? We need a data structure that A, we can replicate, B, that is causally, we can replicate it in a causally ordered way, and C is guaranteed to always converge. So that no matter how many different things happen in all these different servers, that we can somehow merge them all back together and it will be fine. And they will all deterministically come to the same value. We use some kind of like map, dictionary, hash table. So how could we use what we have like just been talking about to make some sort of conflict-free replicated map? Oh, we'll just do this. It's easy. Oh, it continues. Okay. Super great, right? Like, I don't know. I can't read that either. So. No, we can actually do this much easier. So if you're familiar with Go's syntax, this is like pretty standard stuff. We have a shared map, which has its storage, where the key is the origin ID, right? Because remember, we're health checking origins here, which refers to a shared map record, which is a value, which is the status. We also keep a version vector along with the map, which is that server's local version vector. And then we keep something called what's called a VV dot, or a version vector dot, along with each of the individual records. It tells us when that record was written and who it was written by. Okay, so here's how our gossip can work then. All right, so we have our like the bare bones of our data structure. How can we start to like move this around? Well, one thing we can do is we can take that version vector, we can pick a server at random, we can say, hey, here's my version. Here's what I currently have. Here's what my state of the world looks like. And if we have some way of doing this, we could say, okay, well, that server that I just talked to, I'm going to like, based on your version vector and my version vector, I'm going to develop some sort of delta. I'm going to figure out what I have in my map that you don't have in your map. Or what is, there could be new records in the map, but could also be things that have like moved forward since then. Things that have like, the opposite of happened before. Happened after, that's the word. Happened after the version vector that you send me. So we can send that back, and then as long as we have some way of merging or joining or least upper bounding that delta with our map, then cool. We have this like coordination-free, like, I don't know, CRDT, that's the word for it. Right, okay, so here's how this could work. So our gossip request is we just go, okay, send them a copy of our version vector. Easy enough. The gossip response is, okay, so we're going to iterate through every record in our map. If their version vector doesn't have one of those dots that's associated with each of the records, if it hasn't seen that thing yet, if that thing has happened after their version vector, we'll include that in our delta. Otherwise, we just skip it, right? Because they already have that. They've already seen it. All right? So we send that back, that delta. And then we have our merge function, which is slightly more complicated, but actually still pretty easy. So we iterate through every record in the delta. If we don't have that origin ID, that's easy. We just add it. If our version vector includes the dot that's associated with their record they just sent us, well then, okay, there's a race condition there. Like, we already got that from someone else. Cool, so we can just throw it away. However, if their version vector includes our dot, that we have for our shared map record, then we know that we should use theirs, right? Because they saw, at some point in their causal past, they saw the record that we currently have, right? So in this case, we can just go, okay, well, we know that they saw it, and they're not using it anymore, so their thing happened after ours. So we can just merge their record in. And if none of that works to tell us whether or not it worked, that is the point in which we use Rendezvous. That's the tiebreaker for this. Cool. So what we have just developed, what we've just designed in this case, is what's called a delta state CRDT map, which is conflict-free replicated data type, but really, I don't know, it seemed a lot easier than the acronym applies. I don't know. So it's coordination-free, but guaranteed to always converge to a deterministic state. It's basically, if you're familiar with CRDTs, it's like a state-based CRDT, except we don't transfer the entire state with each replication. It's basically just like version, delta, merge. And the reason we can do that is because the causal consistency is actually built into our gossip mechanism. Cool. And a lot of that actually came from this paper, which if you would like to read more is really great. And the papers that came before this, talking specifically about delta CRDTs. Okay. So we've just walked through and designed an eventually causally consistent system using rendezvous hashing for load balancing and ownership, swim via Memberlist for failure detection and cluster management, and causally ordered pool-based gossip for communication, and a CRDT map to provide convergence. However, one of the questions that I would ask at this point, if I were sitting in the audience, would be, why the hell are you talking about this? Why is the CTO of a different company up here talking about how to use these tools to, made by Hoshi Corp to build this? It doesn't really make any sense. So one thing I do care about is the concept of edge compute. It's possible to do so much more than we currently do at the edge. And what the edge means in this case is not oh, it's the CDN. It actually means basically something that is dependent upon your specific application. So that could be actually doing computations in browsers. It could be doing computations in routers. It could be doing computations in cars and airplanes, right? It's a whole wide variety of these things. But the interesting thing about this is that another way of saying edge compute is just saying coordination-free distributed systems, which is what we just built. All the things that have been studied in this field for so many years apply directly to edge compute applications. So why has it taken so long for any of this to catch on? A, it's hard. But B, there's this idea of something called single system image. It's one of the things that holds us back because it's also one of the things that makes development easy. Single system image is an abstraction. It says that a distributed system, regardless of the number of nodes it's running on and where they are, should provide an interface that makes it appear as if it's running on a single computer, a single system. Another way to put that would be to say it's linearizable, again, right? The pursuit of this single system image idea is why we like concepts like leaders in distributed systems. Because another way of, I already said that. All right, meaning that to an outside observer, it appears as if every event had an order. Every event happened one after the other, despite the fact that the real world doesn't work that way. For any two events in a single system image system, you can definitively say that one of them happened before the other. So once you start running your systems across multiple data centers, multiple regions, sometimes even in a single data center, you have to grapple with the fact that single system image, or linearizability, is not always realistic to do, right? It actually provides a hindrance to a lot of systems. It's this, in my opinion, it's this relentless pursuit of single system image that has led us to a lot of bad, hacky distributed systems in the past, right? A lot of times it's useful, sometimes it's not though. And so when it comes to edge compute, this idea of single system image just doesn't work, right? You can't have a single system image that encompasses all airplanes, right? It doesn't work at all. If your self-driving car has to check in with a central database before it can decide whether or not to turn left, everybody's going to have a bad time. So this is why we need new concepts, new education for these things, new frameworks, and et cetera. I'm sorry to keep posting papers here, but I don't know. There's an article entitled "A Certain Tendency of the Database Community" that I should have remembered as I was writing this. But the specific quote is, "We posit that striving for distributed systems that provide single system image semantics is fundamentally flawed. and at odds with how systems operate in the physical world. It's another good way of saying it. So ultimately, what we've walked through today is like building an entirely coordination-free distributed system that still maintains the requirements and the invariance that we required, right? Without having to use strong consistency, linearizability, or single system image. So ultimately what I'm saying is, like, this stuff is actually possible. Like, it's actually like not that bad to build systems like this, but one of the things that we rely on are our metaphors, one of which is single system image. We also need new intuition, like, which is just part of education and learning for this, right? Like, if we always go for, okay, I'll just put a database in it, well, that's, I mean, if that's our intuition, then maybe that has to change over time. Anyway, that's all I got. Thank you.